Online lecture number 20. Last time we spoke about chemical reactions, and specifically we looked at the end of last lesson on a nucleophilic substitution reaction. So a nucleophile attacks an electrophile. It substitutes a chlorine that splits off as a chloride by covalently bonding to this primary carbon here. So the reason why this reaction happens is because the chlorine in the initial electrophile molecule is lowering the energy of the sigma star orbital, which is the LUMO orbital, and that makes the LUMO-HOMO energy match more compatible, and therefore the reaction is favorable. So today we will talk more about such substitution reactions, and we'll classify them in different types. And the first one that I would like to discuss is a SN2 reaction. And here we have a nucleophile, a hydroxide ion, attacking a bromocarbon. So for SN2 reactions, these electrophiles, they can be any halogenoalkane. In this case it's a bromine, it could also be a chlorine. So in the name SN2, N stands for nucleophilic because of the nucleophile attacking. And then you know this reaction proceeds and the hydroxide replaces the bromine that then splits off as a bromide, and that is called substitution. The bromine has been substituted by the hydroxide, so therefore the S stands for substitution. It's a nucleophilic substitution. So the energy profile for such a reaction is plotted here. How it proceeds from reactants to products, and that happens in an SN2 reaction via a transition state where the hydroxide and the bromine are attached simultaneously, but this is really just a hypothetical construct. We can never really experimentally observe this because it's too short-lived, and then it immediately forms the product in a single step, right? So there is no intermediate chemical that is formed. It happens all in a single step for an SN2 reaction. So we can write the equation generally to be like a nucleophile reacts with an electrophile to produce products, and the rate of this reaction is proportional to both the concentrations of the nucleophile and the concentration of the electrophile. And that's because in order for them to react with each other, they need to meet, and they meet and in one single step form the products. And that's why we call this also a bimolecular reaction, because it involves both the nucleophile and the electrophile, and that makes it second order, and the 2 now is in the name SN2 included. So it says a substitution reaction that is nucleophilic and has a bimolecular mechanism, meaning the rate is a second order. So I already discussed with you how the sigma star orbital is involved in this reaction. Let's discuss it a little more and depict it graphically. So here is the lone pair of electrons in a p orbital of the nucleophile, like the hydroxide for instance. And this lone pair is now the HOMO orbital that provides electron density from the nucleophile, so the donating pair of electrons. And as I said, it reacts with a LUMO in the electrophile, in the halogenocarbon. That is a sigma star, and we figured that this must be the sigma star of the CBr, and X stands here simply for any halogen that could be instead of the Br, like chlorine for instance. So here is a schematic of this sigma star orbital. It is an anti-bonding orbital, that's why it has this node here, and it spreads over the halogen and the carbon, and it's empty. So now the lone pair from the nucleophile can be donated into this vacant sigma star, and therefore the energy is lowered. It jumps from here to the vacant orbital, and then it forms a transition state where hypothetically the nucleophile and the halogen are attached through in one line along this sigma star orbital direction. But this transition state very quickly now evolves to form a new sigma bond between the nucleophile and the carbon, and the halogen gets substituted and splits off to form again a molecule with with a pair of electrons in a p orbital, a lone pair. So one thing that is interesting about this reaction is you see the carbons here, they are in a pyramidal configuration, and in the transition state they switch into a planar configuration, and then in the product they are again pyramidal, but this time on the other side. So the reaction involves this swapping, like an umbrella that is blown from the wind inside out from one side to the other, and that's part of what this activation energy costs for this reaction to happen. So what are the effects of the functional groups on the rate of these SN2 reactions? So you remember, if you have a carbon that is surrounded by these R groups, the functional groups, and here the halogen, so you have a partial positive charge on the carbon because of the electronegativity of the halogen. And now these functional groups, they can stabilize this partial positive charge. They can make it less strong. We call this the positive inductive effect. And the methyl groups, if you have them, they reduce the partial positive charge on the carbon by donating electron density through these sigma bonds. So that makes this electrophile then less partially positively charged, and therefore nucleophiles are less attracted to the molecule. So the more of these residual groups you have here, the less attractive are nucleophiles to this molecule. So therefore, if you have no residual groups at all, then this is a more reactive electrophile than one that has already a residual group there, a methyl group that causes a positive inductive effect. But not only this, it's for one hand it's the inductive effect, but also it's the steric hindrance that the residual groups cause. So remember, the nucleophile has to attack the carbon that has a partial positive charge, and in order for it to reach the carbon, it needs to somehow penetrate through these residual groups. But if they are blocking the carbon from attack, then there is a steric hindrance. So the one that has the most methyl groups is the most hindered molecule, and the one that has just hydrogen is the least hindered. So the most reaction, or the highest reactivity, is for the least hindered, and you can see here are relative rates. Let's say the secondary has our relative rate of 1, then the tertiary that has all these steric hindrance is not reacting at all with a nucleophile, while the one that is a primary that has only one methyl group reacts 50 times faster than the secondary, and the one that has no methyl group at all reacts 1,500 times faster than the secondary. So now SN1 reactions. So you've learned now SN2 reactions. They are bimolecular, they are second order and single step. However, SN1, they are actually not single step, they proceed stepwise. So here I plot the energy against the reaction coordinate. So we start with one of these halogenoalkanes, and now this one is going to form a carbocation totally on itself. So by itself the halogen splits off. It doesn't need the nucleophilic attack to split off, it happens by itself. And why is that possible? Because of the stability of the carbocation. So in order for this to happen, still of course you have to overcome an activation energy, but then you end up at a secondary minimum of the energy for the carbocation, and for it to now go back, it needs to overcome this backwards direction activation energy, and the height of that is determined by the stability of this carbocation. So this happens all through this transition state also. So here it goes from a pyramidal to a planar, and then the nucleophile can attack. Now you have the carbocation, and now the nucleophile can attack. The nucleophile here can't attack the reactant here. The reactant needs first to form a carbocation for the nucleophile to attack. And then via an activation energy again and a transition state, you can form the products where the nucleophilic substitution is now completed. But you've seen this time it's stepwise, right? So and generally we can write the nucleophile A and the electrophile B, they react, but the rate of the reaction only depends on the concentration of the electrophile, because that is the rate determining step, the formation of the carbocation. And the formation of the carbocation does not depend on the concentration of the nucleophile. It only depends on the concentration of the electrophile. And therefore it's first order, and the rate of the reaction, of the SN1 reaction, is given only by the concentration of the electrophile. So the nucleophile, once the electrophile has formed the carbocation, then the lone pair in the nucleophile can attack the carbocation, and that's the second step. That's now going over the second bump, but the rate determining step is here forming the carbocation, and that's why it is a first order reaction, a monomolecular or unimolecular reaction. So how do the residual groups affect the SN1 reactions? We looked at this before for the SN2. Now again, it's about forming the carbocation and the stability of the carbocation. So residual groups via the positive inductive effect and also via the hyperconjugation, they can stabilize the carbocation, right? So the more of them you have, the better. So tertiary carbocations that have 3 R groups, they are the most stable, and therefore they are the ones that react the fastest in an SN1 reaction, right? They are the fastest because they form the most stable carbocations that then can proceed to react with the nucleophile to do the substitution. So the less R groups you have, the less stable is the carbocation, and the slower is the SN1 reaction, because you cannot form stable carbocations, right? So comparing the numbers, the primary and the halogenomethane, they react almost not at all, so because they don't form stable carbocations. The secondary can form stable carbocations due to this positive inductive and hyperconjugation, while the tertiary has an extremely high rate of about 100,000 times faster than the secondary because of its stable carbocations. So generally we can say tertiary halogenoalkanes, like this one, they undergo an SN1 reaction because they form stable carbocations, while primary halogenoalkanes, like halogenomethane, they go through SN2 reactions because they make it most easy for the nucleophile to attack. So everything that's in between is somehow a mix between SN1 and SN2 reaction. So now the overview, we looked at SN2 and SN1 reactions. So SN2, even though it says 2 here, it's a one-step reaction, but that's precisely the reason why it's a bimolecular, while 2-step is SN1, and the rate for SN2 is bimolecular because both nucleophile and electrophile need to meet, and so it depends on both concentrations, while for the SN1 it's only the formation of the carbocation that really governs the rate, so it's unimolecular. So now the rate of these reactions of SN2 for the least substituted carbon, so for the primary you have the highest rate because the nucleophile can attack the most easy, while it is hindered by too many R groups to happen, while it's the opposite for the SN1, because the most substituted carbon forms the most stable carbocation, so you have the highest reaction rate for this one, while you have the slowest reaction rate for the least substituted carbon, for the primary. So the rate here for the SN2 is mainly governed by steric effects. So with 3 residual groups, the access of the nucleophile to the electrophile is hindered, while in the SN1, the rate is mostly governed by the stability of the carbocation. So there are some homework for you guys to do. So first, there's one important part to read about, which is about the effect of the solvents on the SN1 and SN2 reactions. And you can read about this on page 936 to 940 in Chemistry 3. And then there are a few homework problems that you can tackle. And I hope you will master them, and see you in the next online lesson.